So this talk is about how to build prototypes for data service automation. A few words about myself. You heard we are building application developer platforms, and in particular, we automate data services for quite a few years now. Started in 2013 and 14 with on-demand provisioning of virtual machines, and now onboarding more Kubernetes operators these days. So we are also building these operators. But data service automation is one of my passions beyond my company. And I would like to share some of the impressions I've collected over the years with you, and then talk about what this means for Kubernetes, and finally, how to prototype such automation with Kudo. So when you talk about data and data automation, there's a variety of things you could understand under that term. And therefore, I'd like to present you with a mission statement, so to say. And that would be fully automating the entire lifecycle of a wide range of data services to run on cloud-native platforms across infrastructures at scale. We'll come back to that definition conceptually throughout the talk, because the point here is the mission statement doesn't state anything about Kubernetes in particular, because technologies change, and data service automation is something that for most organizations who have to create a lot of databases, these databases usually live, many years, and therefore, in the past 5 or 10 years, we've seen multiple platform technologies come and go, including Mesos and Kubernetes, Cloud Foundry, and the likes. So the next thing is, if you look at a modern organization, you will see microservice-based architectures with microservices having specialized requirements for data persistency and data processing and messaging system and streaming systems and so on. So it is very likely that an organization these days not only has more data services in terms of databases to operate, but also different types of databases and more than in the past. So relational database isn't enough anymore. All right. When we talk about what data service automation actually means, and what the complexity in data service automation is, one of the principles when approaching, let's just take a simple example. You have a database such as Postgres, and you want to automate the lifecycle of that on the database, and you want to go through the entire lifecycle. One of the ways to approach this would be to apply an iterative strategy, of course, and start with drawing the outer shape, for example, covering use cases such as how to create and delete service instances. So when I talk about a service instance, I would talk in the context of Postgres. A service instance would, for example, be a Postgres server, let's say a stateful set with a service, or even a streaming replication cluster with 3 pods in a stateful set. So lifecycle managing such a service instance, you'd start with creating service instances, modifying them, for example, to change the minor version from Postgres 12.1 to 12.2 or anything like, creating backups and recovering backups. But you will see that if you really want to enable your application developers with on-demand self-service, so that they can create their arbitrary or that they can create data services whenever they want. Let's say it's 2 a.m. in the morning, they want to do production deployment. Well, they should be able to do that, and it shouldn't require the interaction of an operator anymore. So on-demand self-service, and over the extended lifetime of a database, which could be many years, could be 5 years, could be 10 years, the application as well as the database undergoes various changes. Version upgrades are the more obvious examples, but there are also the expectation that if you do that at scale, so that, for example, if you have hundreds or thousands of these instances, you will also see virtual machine or physical hardware failures that will also have some kind of impact on your data services. So looking at failover scenarios and recovering from those failover scenarios become an integral part of the automation. All right, so that's about a particular data service. I use Postgres as an example, just that everybody can, can picture that data service. And if you know Postgres a little bit, you know also that, for example, clustering Postgres with synchronous or asynchronous replication is a bit tricky, and you will have to add additional components in order to have cluster management, failure detection, so detecting that one of the nodes, for example, has died, and that, for example, your primary node has to be recovered, that you'll have to trigger leader election, and a new primary has to be elected. But this is only part of the story. So in our use cases, when we build platforms, application developer platforms for large enterprises, it's not rare that these environments, they can get very, very big. So we have more than 10,000 virtual machines in responsibility in our operations team. And a lot of more virtual machines are basically operated by the customers using automation products. So the question is, if you look at application developer platforms at the scale where there are thousands of virtual machines, whether they are VMs or Kubernetes nodes in Kubernetes clusters, you will see that in these environments, they contain not only one database, it's not only Postgres, it's a set of databases, let's say a dozen of them, and many instances thereof. So if you think about data service automation, the question is, what is your actual goal? And as I presented early on, the goal in general would be that the automation is made sure enough that you can not only lifecycle manage a single database, but many instances of the many Postgres databases, for example. And if you have multiple operators covered, you can say that in such an environment of thousands, where thousands of application developers create and modify their databases, the automation will cover that job without human intervention being necessary. All right, but this is how to build a development or production grade software. And one of the takeaways here is that scale actually matters. So if you talk about the viability of a particular solution, you really have to think and evaluate what is the context you're applying this. So if you think about that simple task of making sausages for your customers, you can see that there are various different implementations depending on the scale you do that. Data service automation with Kubernetes. We've heard today very good arguments, and I think I'll agree with a vast majority of what has been said earlier. I think Kubernetes is ready to take on to onboard data services. So there's no need to keep entirely a Kubernetes cluster entirely stateless and just deploy your stateless applications to Kubernetes. However, if you look at very large organizations and they want to have a central governance about, for example, how data services are created and what exactly you can configure, the question is, how can you do that with Kubernetes? And some of the answers will be covered in this talk. What I can also say from experience is that we have clients who started enthusiastically looking into Kubernetes, especially to operate databases, and some of them have abandoned these projects. And this doesn't tell a negative story about Kubernetes. It just means that some workloads are very, very specific and have a stronger, let's say, tendency to run on a virtual machine because the paravirtualized virtual machine technologies provide you with a high degree of isolation. So especially for high performance applications where you need control over network I/O and disk I/O isolation, a virtual machine is still setting itself apart from a container. However, with Kubernetes and Kubernetes implementations where this kind of weak isolation is addressed, this, well, let's say affinity towards virtual machines could disappear. And this is one of the beliefs that we also share. So Kubernetes for data services and for data, that's a thing. So first of all, I'd like to talk briefly about what are the stages of developing. So if we approach a new data service, I will present an example of a data service that you potentially have never heard before. It's called SECONDO. If you start developing your own solution because you want to operate that database, we propose to have 4 different levels on approaching that such a project. At first, we need to understand if you talk about a service, a data service, what would a sysop do? For example, Postgres. How do you set up a Postgres server? How do you configure a Postgres server? What are the variables that within the configuration file you have to adapt, for example, to the size of a pod? For example, having a cache that has a certain size corresponding to the memory available in the pod. Once you have that, once you understand how the service works, depending on the service, and Postgres is a good example, you'd have to think about how to cluster it, how to make it highly available, for example, by applying a replication strategy. In Postgres, for example, let's say asynchronous replication, so that you'll be more robust against slight delays in networking, so that you don't prolong individual transactions if there's a certain lag between the nodes. So you're writing to the master, and at some point, the secondaries will actually be up to date. So if you think about building such an automation with Postgres, you also have to set up a streaming replication that requires setting up replication users, authenticating them, and also a cluster manager. So something that detects if one of the nodes is down and triggers leader election and all that. So having that knowledge together, how would a human operator operate a data service is basically what here is called operational model level 1. So once you know that, you'll start containerizing your application, and assuming that there's already a container image, you start creating YAML specifications and apply kubectl to manually build your service instance until you find that, well, there's a service, there's a stateful set, there's a config map, you have your stuff together. And at this point, you're ready to enter level 3, where you build an operator. Now, I call this operator. We know that the operator SDK is not the only way to integrate data in Kubernetes and data automation in Kubernetes, but I think the term has been spread quite, and it's quite popular. So once you have the operator will basically provide custom resources so that you can talk to the Kubernetes API to create a Postgres database, for example, and configure it and interact and go through the use cases of such data service instance. Now that's nice, but if you think back, if you think about an environment where you have potentially not only 1 Kubernetes clusters, but let's say 500 of them, and a large organization has easily that number of Kubernetes clusters, then you also have to think about how do you do release management for your operators, and how do you ship operators into these environments so that application developers can update their service instances, let's say in the event of a patch level version upgrade, as quickly as possible. That's why operational model level 4 is important. You also have to deal with lifecycle managing the operator itself. When talking about automation, the operator SDK talks about different maturity levels. I think it's a good orientation. In particular, I'm not really convinced that this is the best categorization and prioritization of use cases you could come up with, but it's good for orienting. So this is how you can judge whether in automation, has some meat to it, or whether it's just day one operations and it will leave you with a lot of headaches if things go wrong. So this leads us to the question, all right, we know actually what the operator should do. It should be able to create several service instances. We should be able to do that by creating Kubernetes objects. And but still the question is, how is this actually implemented? And to cut down to the point, there are at least 3 ways I can think of. The most generic way would be to use Kubernetes CRDs, where you tell the Kubernetes API, well, there is a new type, let's say a Postgres object, and the Postgres object has a number of replicas as a parameter to describe whether it's a single or a clustered service instance. You can also specify a Postgres version and that kind of stuff. So how do you declaratively describe how that particular service instance should look like? That will make up the data structure you specify as your Postgres CRD. Now, once you apply the CRD to your cluster, the cluster doesn't know how to do anything with it. It stores that object. It knows you really want to have such a Postgres object, but in order to make that happen, you need a controller. So the basic way on how you could implement that would be custom resources and custom controllers. There's a framework written in Go. It's open source. I think it's also part. It's a CNCF sandbox, or at least a sandbox project. I'm not sure about the particular status at the moment, but the Operator SDK is a way on how to approach building and specifying CRDs and custom controllers. All right, so that's nice, but you either have to use Helm charts in there, which limits what you can do with it, or you can use Ansible or Go code, while Ansible and Go code options will provide you with the, well, let's say, biggest flexibility. Now, in our own journey in building operators, we started with the assumption that the Operator SDK will be sufficient to build these controllers and CRDs. And we've recently learned that some of the more opinionated assumptions in the Operator SDK, they actually create restrictions that are undesirable as well. So depending on how deep you want to go into the rabbit hole, even the Operator SDK might create some restrictions for you. And now there's Kudo. Kudo takes a different approach in that sense that it's not something that is more like, it's not a framework in the sense that the Operator SDK is. You don't have to do programming. All you have to do is declare an operator. So Kudo provides you with the operator manager, which is a generic component, and all you provide the Kudo operator manager is a declaration how the operator builds service instances. And that's a very interesting and neat concept, and there are very nice abstractions in Kudo that are worth looking at. So I can just recommend everybody looking at Kudo, not necessarily because you want to use it to automate the most important database in your company. I would discourage that, but it's absolutely interesting to see how it works. So Kubernetes, as I said before, CRDs, this is basically describing a data structure that you'll teach the Kubernetes API. Kubernetes will then have or offer an endpoint to create objects. Here, for example, we describe a Postgres object, as I said earlier, specifying properties such as replicas and Postgres version. If once you apply the CRD, you can then specify objects according to that CRD, custom resource objects that are compliant with the custom resource definition. But again, without a controller, you basically store this information in etcd within Kubernetes, but nothing happens. So the magic actually comes with adding a controller. Here's a bit of code taken from an exemplary Operator SDK code where you basically watch for such an object to emerge. So if such a Postgres option, for example, object is being created, you would then trigger a reconcile loop. You would basically find out, is this a new object? Yes, which means that the secondary resources you want to create, that would be, for example, let's say a service, a headless service, and a stateful set for creating a Postgres instance. And that's basically what the code does. It creates secondary objects based on the specification of the primary object. Primary object Postgres, secondary objects would be a headless service and a stateful set. I know this is a bit simplifying. So here saying that a Kubernetes controller translates primary resources in secondary resources automatically triggers the idea that the secondary resources can only be Kubernetes native resources, such as stateful sets or deployments or replica sets or pods or jobs. But this is not the case. So for example, in our implementation of Postgres, we have abstractions for service bindings, which means the connection of an application with a data service to make that more comfortable, as well as for backups. And you can imagine that, for example, if you create a backup, well, you could use jobs underneath, but you could also create a CRD where allowing application developers to create, for example, a service binding, and then for a service, for actually reconciling the service binding, you could connect to a database and create a database user there based on a secret that you've created earlier. So this is an example where reconciliation of a primary resources will also modify a non-Kubernetes native resource on behalf of a controller. All right, so this is where Kudo comes into the game. Let's assume we want to build an automation for a data service that's more experimental, which I'm doing in my spare time. I'll come to that example a bit later. And this is where the Kubernetes Universal Declarative Operator becomes handy. It states that you can focus on your software, you don't have to know much about Kubernetes, and it's also for day 2 operations. Well, I would disagree a bit with that, especially with the day 2 operations part of it, because it limits what you can do with operators a bit, but that's not a big problem. It still has a lot of purpose, in my opinion, and it's fun to use, definitely usable in those level 2 and level 3 stages when developing operators and when developing automation. So let's assume you have a rather complicated data service that requires a lot of different Kubernetes objects to be created when you create a service instance, and you want to create an object, an operator that does that for you and makes that easy. I'll give you an example. This is an experimental database I'm working with in my spare time. It's a monstrous database with, I think, 2,000 different operators built in, and database operations built into the database. It's a graph database. It's a key value store. It's a relational database. It does do things on disk. It does do things on memory. It has spatial extensions and spatial temporal extensions, where you can basically modify and model phenomena such as polygons, shapes that will evolve over time. So imagine you have, let's say, 2 forest fires, and you want to model the forest fires as they evolve over time, and then query where the firefighter, which is, let's say, a moving line or moving point, and you want to query where this firefighter has been closest between the fire. So this is something that database can do. And in order to make large data process or query across large data sets, you want to set it up as a distributed system. So in this picture, you can see that a single data service instance, which means a single distributed system of SECONDO for one use case, already consists of 4 stateful sets. In this example, we have 2 different groups of stateful sets. The left stateful set is basically a master node that coordinates a MapReduce like interface and processing of queries, and the second set is a replication service that allows for intermediate data to be stored in replicas, including indices of the data of the database, so that if individual nodes fail, the query can still be continued. Just assume that you have a large data set and the query will run for hours, and therefore the probability of failing nodes increases with cluster size. So we need to create 4 different headless services. We need to create 4 different stateful sets and even a bunch of config maps, which are left out for the purposes of this presentation. Now, this is where Kudo becomes fantastically handy. But before we dive into the details, once you have declared your operator, this is how you can create and install such an instance. So if I just take that command and paste it here, you can see that one after one, this service instance will be created. This is, for example, the original master, which would be the distributed to master here. So it will take a while, and one after one, it will create the other resources as well. So you can see the workers are being created, which is the second stateful set, and along with that, you would see the pods will be created. Sometimes these things have to restart because there are some race conditions in the implementation. It's experimental, as I said, but they will come up and be alive. No, it's persistent volumes being provisioned. Well, that's fine. All right. So this is what Kudo basically does once you have configured it. So the question would be, how does it work internally? Well, just for completeness, deleting such a service instance is also just a one-liner. Deleting the persistent volume claims, I didn't put that into the operator because sometimes I really want to reuse them, especially for experiments with that database where I have to do partitioning and loading a lot of data that takes a lot of time. Reusing the disk is sometimes saving a lot of time. All right, so the workflow in Kudo is basically simple. You create YAML files. The first thing is operational model level 2. You create the stateful set definition, right? So here's the stateful set definition for the original master, the original worker, the database service master, and the database service workers. Those are the 4 stateful sets. Now, this is a standard Kubernetes YAML with a little bit of templating in there. So straightforward. It's just pasting your YAML files into that template folder, apply a little bit of templating, and then you create a so-called operator YAML, which would be the second part of building a Kudo operator. And as you can see here, building such a complicated service instance is not more than 103 lines of YAML code. It basically breaks down the creation of the service instance into a sequence of applying tasks against the Kubernetes API. So the tasks are here defined, for example, create services. And this create service task breaks down into kubectl applying this file, which refers to the service definition contained in this file. So it's really simple and straightforward. So we'll do that with the stateful set definitions and everything alike. And the process of creating a service instance is then formulated as a so-called plan, which the specific plan is called to deploy. It applies a serial strategy, so you can always, on this level of the plan, determine whether the phases, which is the smaller unit, will be executed sequentially or in parallel. Each phase is then subdivided into steps, which then map to tasks. And for each phase, you can determine whether to execute steps sequentially or in parallel. So If you want to boil it down, at this point, Kudo is a workflow engine for applying kubectl specs, YAML specs with kubectl. If you want to boil down Kudo to one sentence, this is what it does. What it doesn't do for you, for example, is generating config maps. So if you have config maps in a format, for example, here I have the script where the actual database script is contained, the experiment, so to say, with a sequence of SQL queries to be executed by the SECONDO distributed system, and I want to move that as a config map to the data service instance. I don't want to go through the overhead of having a container image because there's a high rate of change in that script during the exploration phase. So in order to provide a config map that can just be applied by Kudo, I use customize, and well, hate me for it, but I'm using a makefile to execute customize. So customize basically compiles config map from files in the file system. It copies them in the Kudo operator directory, which would be here, and such a config map looks then similar to this. So it's just customize basics, used in a makefile, generate that config map, and then this config map is referred to here by a task, and the task is just applying the file. So it's simple. All right, let's have a glance what Kudo actually did. So you can see the service instance is up and running. So there's no workload there. We don't have to log into the database here. But the point I was trying to get to is, with a bit of YAML, we described a fairly complex service instance. And for example, when I'm doing research within the database, so I'm recompiling extensions to the database, which I develop in C++, and I do that regularly. So I want to create a service instance, rerun an experiment, and so on. And I don't want to run this database for an extended amount of time. I don't need backups. I don't need monitoring. All I want is create those resources and destroy them rapidly within my experiments. And I cannot think of a faster way of getting there than to use Kudo. So a few of the limitations I've already mentioned. It's an alpha version, which means that it is subject to change. It will break the API, so you may have to touch your operators or operator specification from time to time, or redeploy the operator manager. Lately, there wasn't so much activity in the repo, so I'd have an eye on whether it's been actively developed. But assuming that the company behind there also has other tasks to do, I would assume that they will revisit Kudo after an extended period of time, and it is still a viable project. Now, in our example, the operator was exactly doing what I mentioned earlier. All it did was creating secondary resources that are native to Kubernetes. So we didn't do a service binding where you have to create a database user. We didn't do a backup where you have to somehow access the database and write to the local file system and move files to an external object store, anything alike. And under these conditions, Kudo works perfectly, and it's very simple and straightforward. If you want to go and deep down the rabbit hole and create custom user behavior, for example, provide custom status fields in your controller, this is something you can do. Although the status fields provided by Kudo are already, let's say, expressive in the sense that Kudo has its own CRD. It's called instances, and you can basically get such an instance and look at it. And as you can see, the status field already is complete because the workflow is complete, and you have a planned status which is more closely related to the plan definition, and it will show you exactly which step is, for example, pending or has failed, so that you can dig into the individual problems if they were to be observed. Yeah, non-native Kubernetes, we covered that. Yeah, as you can see now, the CRD that comes with Kudo is called instances. In the operators we've built, you have for a single data service multiple CRDs. For example, for backups, for backup plans, for service bindings. So and each service itself has its own CRD, because the design of the CRD, the way you specify your Postgres object, for example, is part of the user experience for the application developer in Kubernetes and should be designed carefully. And this is something that's not really encouraged in Kudo, because they are all called instances after you've applied your configuration, and it's a bit cumbersome to create those objects. And let's say it's well, you could even call it non-idiomatic in Kubernetes. So designing CRDs is not really possible, and it takes away an essential thing that I think to designing operators is actually, it's important. Another limiting factor is that only one plan can be executed at a time. And if you think about the introduction, if you're looking at many Kubernetes clusters or many operators within a single Kubernetes cluster, that could be at some point limiting. And I don't think it's meant to have that thousands of data service instances scenario covered that we see for some of our clients. And that's okay. It's not to blame anybody. It's just, it's a tool. It has its place. And I think prototyping experimental automations is, for example, a wonderful match for Kudo. All right. So building data service prototypes with Kudo is simple and straightforward. I recommend it. Executing YAML specs in a workflow style. So you see the phases and the plans and the phases and steps are then basically mapping to tasks. So that's an interesting abstraction, and it's much simpler than to paste and cut and paste into Go code, where you specify your structures in operator using the operator SDK, for example. So if all you do is creating those resources and deleting them, Kudo, I love you. All right. So, and as I said, if you really want to dive deep down into the rabbit hole, then Kudo isn't for you. You potentially want to go with the operator SDK or even with bare CRDs and controllers. But I think the operator SDK is a good place to start. So thank you very much for your time. I hope you enjoyed the journey.